Hi everyone. So this is the second edition of reading the research paper with the author himself. I'm very happy to have Zachary with us talking about scaling law for DiLoCo. So this comes like in very timely, I would say, moment because at Hugging Face we're trying to push the Boom project, which is trying to train big models across multiple data centers and scaling laws for DiLocos. I mean, this is the perfect paper for us. So we'll let you introduce yourself a bit, and then we can discuss the paper.
Awesome. Thanks for joining. So yeah, I'm Zachary Charles. I'm a research scientist at Google. Uh, I was a mathematician for a while. I got a PhD in applied math at the University of Wisconsin-Madison, and slowly found my way to Google because I started doing kind of distributed optimization, machine learning
Mhm.
postdoc, and have really never left the field since. At Google, I joined the team that did federated learning, and that has kind of naturally progressed into thinking about, well, what about algorithms like that we use for federated learning is useful for training LLMs in the data center. And this means that there's just a lot of
Um,
commonality. The DiLoCo algorithm itself is essentially a version of an algorithm that was independently developed for federated learning. For those who don't know federated learning, by the way, that is trying to train a model collaboratively, usually across a bunch of smartphones or edge devices without sharing data. Um, and communication efficiency, just like it's important for kind of data center training, it's also very important for federated learning, and that's kind of the transparent on here. Anyways, but started working on DiLoCo, and the fundamental thing that happens when you talk to machine learning people about DiLoCo is they recognize immediately, hey, this is changing the dynamics of the learning algorithm, which is correct. It's not kind of standard data parallel SGD. You have this averaging step, which is fundamentally kind of discontinuous from the rest of the SGD stuff, and that makes people nervous sometimes. There's been so much work into developing understanding of kind of dynamics of SGD and related algorithms, and showing that it scales in this way that's very, very predictable. And so basically, this work was motivated by the desire to have exactly that for DiLoCo. Based on a bunch of work, including from people from Hugging Face, Prime Intellect, people at Google, various papers kind of confirmed, hey, this works at the 500 million parameter scale. This works at the 1 billion parameter scale. This works at the 10 billion parameter scale. But those are kind of isolated incidents. And the fundamental idea behind scaling laws was that, well, we should actually do a ton of different model sizes at once and really try to understand, is the performance predictable? And that's exactly what we set out to do. Take DiLoCo, try it across a bunch of different models, really tune it as much as humanly possible. We ran just a phenomenal number of experiments to do this, and tried to predict various aspects of how it behaves as model size increases. And show, this is kind of the goal, to show that it behaves as well, if not better, than data parallel training in some respect, while reducing communication costs. So that is the maybe 1 minute intro to it.
Perfect.
But yeah.
And yeah, so as we see, there's it seems like to be like three main contribution to the paper. But before we goes on
Yeah,
explaining the key four findings, maybe we can do a small recap about what is
yeah.
DiLoCo, like 'cause
Uh,
a small recap.
that is a
Yes.
great idea, and potentially should have done it before. DiLoCo is quite a simple algorithm. I think there's a lot of different tricks and things that people have now added on top of it, but fundamentally, it's pretty simple. This idea that we want to train with less communication. So, data parallel training, you have to synchronize kind of all your devices after every single SGD step. And
Mhm.
we're basically just going to relax that. We're going to say, instead of training across different GPUs and synchronizing them at every step, we're going to train independent models, maybe on a cluster of GPUs in one location and a cluster of GPUs in another location. In this picture, it's 4 different locations. So we have 4 separate copies of the model. We train them independently. They're not communicating with one another. They're seeing different data. And then every H steps, we synchronize the model weights to make sure that the models are somehow benefiting one another. Um, this picture does not say synchronization, it says outer optimization. That is the one thing that's very, very important about DiLoCo, is just naively averaging models across these different kind of compute clusters. Not good enough. We end up having to do something where we inject kind of long-term momentum from one synchronization period to the next. So we can talk about that in more detail, but secretly, every single time we do synchronization of model weights, we inject actually an optimization step in order to kind of do momentum, in addition to kind of synchronizing the models. So,
Okay.
but that's basically it. You can reduce communication this way by a factor of h, right? Total communication goes down. Instead of synchronizing every one step, you synchronize every h steps, and that's why it reduces communication and trains faster.
Okay. So yeah, okay. And this is a nice recap of like DiLoCo. And so now there's like 4 findings. So let's find like, so can we like maybe just like talk about like maybe all the experiment you have like run so far, like for example, like
Yeah.
the scale and stuff before like we delve into the findings so that we
Yeah.
know. So maybe
So
like I think the page like 6, if you can like click on me.
yeah, well, before we go to that, actually, I would
Okay.
love to pull out the tables right above the picture of that logo, because that's
Ah,
going
yeah,
to
the
be
notations. Yeah, yeah, I think it's important
yeah.
as well.
So there are a couple things between DiLoCo and data parallel that are shared. They both have model weights. They have a model size. You compute some kind of valuation loss. You have a number of training steps, so on and so forth. And they both have what we call an inner learning rate. So that's the inner learning rate you're actually doing when you're doing kind of each of these gradient steps. Typically, that's the inner learning rate that's applied to something like AdEMW.
Mm-hmm.
They both have a batch size too. I will note that batch size interpretations is slightly different. For data parallel, it's your batch size. For DiLoCo, the batch size is the sum of batch sizes across all the replicas. But DiLoCo has some extra parameters, which are going to come into play later in the experiments. It has the learning rate we use during the outer optimization step. It has the number of replicas that we are training over independently, and it has how often you're synchronizing. So keep that in mind. These methods are very similar, actually, but there are important differences between them. Okay, so let's go to the table that you mentioned, because I can just kind of set up maybe at a high level how you end up doing, basic scaling law experiments. And the first ingredient, you just need to train across a bunch of different model sizes. Scaling laws at its core are that we are going to try to predict something about the model as the size of the model varies. And so what we did is we took data parallel, we took DiLoCo, applied them to 10 different model sizes, ranging from 35 million parameters to 10 billion parameters. Various details about the transformer architecture, if you're interested. The details are all in the paper. And for each model, we used the token budget that the chinchilla scaling laws says is optimal for that model size. So we're not trying to rederive kind of how many tokens you should use for each model size. Everything that is a given. But then within each model size, we basically just do a bunch of different experiments varying the hyperparameters and the number of DiLoCo replicas. And the goal is to first make sure that everything is completely well tuned. And then second, we can see kind of how the behavior changes, not just as model size changes, but as the number of DiLoCo replicas changes. So there's kind of two different scaling factors going on. Model size, which we usually call N, and there's the number of
replicas
we call M. So that's going to come later. But then once you have that done, it's a pretty straightforward thing. You just run a bunch of experiments and you collate all the data. Well, note one thing, experiments are expensive. So we tuned up to 2.4 billion parameters. Then we developed our scaling laws, and we use the scaling laws to predict the optimal hyperparameters for the 4 billion and 10 billion parameter models. So this column here, this hyperparameter sweep says, okay, we are actually doing tuning on models up to 2.4 billion parameters. And we use 4 billion and 10 billion parameter models essentially as like held out models, models that we're going to extrapolate to with our scaling law to see how good is our scaling law.
Okay. Okay, so now that we have like all the setting and stuff, maybe we can like talk about the first finding, which is the scale. So page 8.
Page 8. Yeah. So the first is a pretty simple but really, really important finding. It's just the fact that DiLoCo actually seemed to improve in its performance relative to data parallel training as the model got bigger. So if you just plot evaluation loss, and this is evaluation loss when you're using the optimal best tuned hyperparameters as a function of model size, and we're going to do this for data parallel and DiLoCo as we vary the number of replicas that we're training over. You can plot it, and there's not a lot to be gained from this plot. They all look kind of similar. The loss predictably goes pretty down as the model size increases. Instead, what's very useful is to look at the right-hand plot, which is not the absolute evaluation loss, it's the relative evaluation loss, and it's relative to parallel training. So data parallel training is at 0. So there's 0% difference between data parallel training and data parallel training.
Yeah.
DiLoCo is different. It has different characteristics in terms of evaluation loss. And I'm going to go into the difference as a function of number of M. But the first trend that you can see is just that that number goes down as the model size increases, which means that DiLoCo is getting better relative to data parallel as model size increases. Now, it is also getting worse as you increase the number of replicas. You're kind of sharding the data across more things. There's just less signal being transmitted. And so you can see that M equals 8 is this top line here, and it is worse to some degree than M equals 4, which is worse than M equals 2, and it's worse than M equals 1. Now, I should note M equals 1 is kind of a weird algorithm. We'll talk about that more in the next finding. But M equals 1 is not a communication efficient algorithm. It's basically the same as data parallel, but it has that outer optimization momentum going on. So more about that later. But the cool thing is we start to see that even at 2 to the 31, which I think is like the 2.4 billion parameter model, DiLoCo with M equals 2 starts to do better than data parallel. M equals 4 is pretty close, and M equals 8 is a little bit of ways, but you can see that it'll catch up as the model size increases more if we had infinite compute.
But I have this question. Do you have some intuition to why, as we increase the number of replicas, the evaluation loss is kind of like, is less good than like data parallel? Is it because we have so many replicas, so each model are kind of like diverging, and so the average is like taking into account the divergence of each training step, or maybe like maybe
Yeah, so I think it's worth thinking about kind of the infinite case. So I'm a mathematician by training, and so one of the ways that you do math is you think about limits. You think about what is kind of the stupidest case, and what is, as something goes to infinity. And think about DiLoCo when M starts going to infinity. We're fixing the token budget. That's a really important thing. So if you have, let's say, 10,000 different models training independently, your token budget is fixed. That means each model is going to see a tiny, tiny, tiny number of tokens. Okay. We're trying to compensate for that behavior by putting those models together and synchronizing in smart ways, but there's a limit on how good we can actually do. So as like a really dumb case, imagine you had 1 million models, each of which sees a single token. That would be really hard to form a good model from. So that's kind of in my sense of why things get worse as M increases.
Interesting. Okay. Then that means that a way to fix that would be like if we have a lot of replicas, to synchronize more often, but maybe like not everyone, but just some of them together, and later, I don't know how to explain that, but
I think you're absolutely right. Like more generally, compensating for this behavior by figuring out better ways to merge them, better ways to be adaptive about when to merge, merging more often as the models kind of diverge, and merging less often as if they kind of have similar optimization trajectories. These are really, really good ideas, and there's something that the community probably needs to deal with.
Okay. All right. Interesting. There's if we move on a bit, there's this table that summarize, I think, better the relative difference, table.
This table is basically just a tabular version of this plot. One of my co-authors, Keith, also former mathematician, so a lot of former mathematicians working on this. He despises plots and loves to just get information from tables. So exactly the same as before. This is kind of as the number of model parameters increases, the evaluation loss goes down for DiLoCo, and the relative error with respect to data parallel also goes down. So same information.
Okay. So I don't know when you plan to talk about the difference between DiLoCo and DiLoCo with one replica and data parallel one.
Let's do that now, because I think that's going to lead into the next finding. So
all right, okay.
Let's go back to that picture of DiLoCo. Actually, that might be helpful in this conversation.
Right. So yeah, page 4.
Yeah. So imagine this picture now when there is just a single replica. So we're not synchronizing across 4 replicas. We just have one replica going. And so there's no actual communication going on. I just have a single cluster of GPUs. I'm training my model. But what's happening is every H steps, I do what's called this outer optimization. This is something that's not present in data parallel. And what this outer optimization looks like, instead of doing momentum where you capture individual gradients, we capture the entire trajectory across those H training steps and put that into our momentum buffer. So it's kind of interesting. It's a very long form momentum that captures trajectories instead of individual gradients. And we apply this momentum step. So we do H kind of standard data parallel steps and then one big momentum step. And that one big momentum step we find is actually incredible. It actually just improves evaluation loss for data parallel training, which is really, really, really nice. I'll note this is like maybe not that surprising. There was a recent paper. I'm going to butcher the pronunciation. It's called the AdEMAMix optimizer. People may have seen it. This is some really, really great work that uses two different momentum buffers. One is kind of a short-term momentum buffer, and one is a long-term momentum buffer, and they find that this also helps. And this is very similar in spirit, not in the actual mechanical details, but in spirit, it's very similar to why DiLoCo with a single replica is doing better than data parallel in some cases.
So if I remember correctly, it's like, correct me if I'm mistaken, it's like there's like a fast like phase of learning, and then like there's the slowing down phase of learning, right? Something like this.
Exactly. And so you can kind of think of the inner steps as the fast phase, and this kind of momentum that kicks in every H steps, let's say H equals 30, as the kind of the slower momentum. It operates differently, of course. These are different algorithms in some sense, but they have, I think, a morally similar observation.
Okay. So maybe we can like move on to the finding 2, which is so single. Yes, okay, I understand better why you
exactly. This is a good segue into it, because finding 2 is quite simple. It's just that single replica DiLoCo. This is the single replica case where you use this long-term momentum. It just attains lower evaluation loss than data parallel training across model scales. And I'll note that we didn't just look at evaluation loss in this work. We also have kind of zero-shot downstream evaluations. We tended to plot HelloSwag because that one had the least variance, but results are pretty consistent across them. Basically, if you compare evaluation loss or the zero-shot accuracy, kind of whichever is your favorite metric, and you look at different model scales and you compare data parallel with DiLoCo M equals 1, 2 things are true. First, DiLoCo with M equals 1 is always better. Sometimes it's only slightly better, but oftentimes if you increase the global batch size, which is kind of what's here on the x-axis, DiLoCo M equals 1 starts to be much better. This is this observation that data parallel training, you can't have the batch size to be too large. You start to generalize badly. And for some reason, DiLoCo with M equals 1 that has this long-term momentum is much more robust to very, very large batch sizes. So performance degrades less quickly as the global batch size increases, which is really nice. It means that you can train more horizontally instead of kind of in serial and get kind of a faster clock train.
Yeah, so that means like we can like pretty much like replace distributed data parallel by just using DiLoCo. And we can get with the benefit of having a global batch size which is way bigger and a good eval loss, which is interesting.
Yeah. I'll note that global batch size here is measured in terms of tokens. If some people watching this are confused as to why it looks so large, the sequence like the 2048 throughout. So if you want to transfer this into like a number of sequences, just divide by 2048.
Okay. So this is like the second finding. So and then the third finding, maybe this table. So we talk about this. I think the table 5. So we don't talk about the table 5. Maybe it's interesting. Like if it's transferred to like to larger scale.
Yeah, this is the fact that the previous plots I was showing you, they were all in the kind of, we did all the hyperparameter tuning in the world, not quite all of it, but we did a lot of hyperparameter tuning to try to optimize performance. We'll talk about maybe scaling laws later, but when we use the scaling laws to extrapolate hyperparameters to these larger models and just ran those, they work well. And we found that DiLoCo with M equals 1 or M equals 2 were both better than data parallel at these 4 billion and 10 billion parameter model scales. So, and for what it's worth, DiLoCo with M equals 4 was quite close. It's still a little bit worse than data parallel at those scales, but 0.18% difference is not that much in the grand scheme of things. So,
Yeah, especially if we see later the bandwidth maximization. I mean, like we see like the compute utilization after. I think it's worth.
exactly.
Yeah. So yeah, finding three about optimal batch size.
Yeah, this is just an extension of what we saw for the DiLoCo M
Yeah.
equals 1 case. So DiLoCo M equals 1 was more robust to larger batch sizes, and that's true for all DiLoCos, no matter how many replicas you use. Actually, DiLoCo M equals 8 is the most robust to large batch sizes, but its performance is worse overall. But it's kind of a nice thing. You can say, hey, for a given global batch size, imagine you were saying, I want to train a model, and this is my batch size because this is how many GPUs I have. You can just look at this plot and say, well, which method is better for me? And if your batch size was 2 to the 20 in this case, so 2 to the 20 tokens at every step, you would look at it and say DiLoCo M equals 1 is actually the best. It's better than data parallel. And DiLoCo M equals 2 is actually still better than data parallel at this global batch size. And one other thing I'll note about this is that qualitatively, data parallel training just has a much sharper spike in loss as global batch size increases. So again, this is this kind of robustness of DiLoCo to large batch sizes.
Interesting. Okay. So yeah, that's the instage direct extension of finding, which leads us, I think, to the wait, where's that extension for? I don't on the right. Yeah, auto learning rate. Maybe do we jump directly to learning finding for?
Yeah,
I feel like
here.
yeah.
Well, finding four is pretty self-contained. I think we can actually just go to the table. It's in the middle column at the last row.
Yeah, this one. Yeah, I have some question as well. That was a bit weird, but
Yes. So this is a pretty simple table. So we've talked about outer momentum multiple times today. This fact that we're doing this outer optimization step every 30 or every H steps. The learning rate involved in that too, and we've been tuning that throughout. And that's an extra hyperparameter that data parallel doesn't have. So you could say, well, maybe DiLoCo has all these benefits, but it introduces extra hyperparameters, and tuning hyperparameters is the bane of most people's existence. But the good thing is that this extra hyperparameter is incredibly easy to tune. And the reason it's easy to tune is that it basically seems to be constant with respect to model size. So we have model size on the x-axis here. We have the number of DiLoCo replicas on the y-axis here. And each cell represents the optimal outer learning rate that we found. And there's a little bit of variance in some of the smaller model scales, 0.4 versus 0.6 in the bottom row. But you can see that once model size gets sufficiently large, the outer learning rate is basically constant with respect to model size. The optimal outer learning rate, you can just tune it for a very, very small model and then just say, this is going to work for all my large models. This is a really extreme form of kind of the mu-p stuff that people use to transfer hyperparameters from small models to large models. This is basically the best case scenario where you just tune on a small model, you do no thinking whatsoever, and you say, this is going to work on the large, which is really, really handy. So yeah,
but
this is kind of just a nice bonus finding.
What I find a bit weird, and maybe you have like the intuition about it, is like why, as we increase the number of replicas, the auto learning rate is like increasing.
Yeah, this is a really good question, and it's one that I've actually thought about for longer than I'd like to admit because it came up in some work I did in federated learning. The fundamental thing to think about here is that these models are really high dimensional things. They're millions, billions, maybe trillions of parameters. And the way that the outer optimization works is we're averaging a bunch of trajectories. And the trajectories, it's a billion parameter models. These trajectories have had time to diverge from one another. So basically, you're averaging this trajectory and this trajectory and this trajectory. And the thing to think about, it's very hard to visualize more than 2 dimensions. But in high dimensions, basically everything is almost orthogonal. So you're averaging these trajectories, they're nearly orthogonal. And when you average a bunch of nearly orthogonal things, you get something really, 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 really tiny. And so what's happening is the outer learning rate needs to compensate for that. for math nerds out there, this is a very nice statistical property of like a Gaussian. You take a bunch of random Gaussian points and you compute their empirical mean. But what's going on here basically is the models are diverging, their trajectories are orthogonal, and we need to compensate for that by using a larger learning rate.
Okay. But I mean, I'm not a math person, but it feels like there's like a kind of a limit that we reach quite easily with like the number of replicas. It seems like we need kind of like more granularities or maybe like more optimizer steps. I mean, not optimizer steps, like for now, DiLoCo is like a B level optimization. Do you think that it this result shows that we need like a N level of optimization? I don't know how to say that, but
Yeah, so I think this was done, I might be misquoting it. Anyways, people have thought about hierarchical kind of optimization as well, right? Like you could imagine
okay.
first doing optimization across two different models and doing that across every pair of models and then doing a level on top of that and a level on top of that. I think this is one particularly promising direction. The other I'm going to note, I'm going to challenge people about this. Averaging is dumb. It's the most dumb thing in the world, and yet it works incredibly well. I don't know why. This is like a fundamental thing that comes up everywhere. Mini batch SGD, we average gradients. DiLoCo, we average things like every single time you're faced with a deep learning problem. Averaging seems to be quite effective, and it is not clear to me why that is the case. We need to move beyond the average for DiLoCo for exactly this problem. Once you're averaging across a million different models, each with their own kind of orthogonal trajectory, maybe averaging is really bad, but I will note that so far averaging is the king of everything. I just have seen very few papers that have done non-averaging type mechanisms and found good performance, unless they're really willing to do a lot of work on top of that.
Okay. Interesting. Okay. So I think the table in itself is quite self-contained. Do we think that we have to move on like the ablation part? I don't know if it's like interesting or not.
So yeah, I maybe just really quick to say, all the results that I've quoted you so far, we actually fixed how often they synchronize. It was every 30 steps. And I'll just note that we did ablations to see how behavior changes as a function of how often we synchronize, and it changes very, very predictably. So how often you synchronize changes the optimal outer learning rate, but again, it's still independent model size. So basically, I think that the TLDR is everything that I've said is true, kind of no matter how often we synchronize. Just you have to kind of shift the parameters up or down depending on it. But the same qualitative observation, every one of the four findings that we went through, it's still true if we did synchronization every 5 steps or every 100 steps instead of 30 steps.
Okay. I think going on to the compute utilization, I think this is for me the like one of the interesting part. But I mean, in my case, because I like compute utilization, but this infrequent synchronization works better for larger model, and maybe you have like some comments about it.
Yeah. So synchronization frequency again is just how often we kind of smash our models together. And this is a plot of evaluation loss for DiLoCo. For a couple models, we saw other models as well, but I just plotted 3 for kind of conciseness. And this is evaluation loss as a function of how often you synchronize. And I'm going to ignore the 1 point for now, but looking from 5 up to 300, you see that evaluation loss increases slightly as you synchronize less often, which is to be expected. If you synchronize less often, they're evolving more in parallel, they're diverging more. So it's harder to get a good model. But if you look, as the model size increases, it looks like we have fewer issues with kind of increasing synchronization cadence. You kind of increase synchronization cadence more for free. So that's kind of this trend over here. You can see that difference between synchronizing every 5 and synchronizing every 3 rounds much smaller, which is nice. It means that the largest models, we might be able to get away with synchronizing every 500 steps, for instance.
Okay.
The one exception, this row, synchronizing every step is bad. And the reason it's bad is also the reason that DiLoCo M equals 1 was good in some cases. It's this outer optimization momentum thing. Does not work well when you're doing it every round. When you're doing every round, it starts to interfere with the dynamics. It doesn't have a good estimate. It's kind of like a badly tuned AdEMAMix optimizer. So it really only makes sense once you start to actually have multiple steps that you're tracking. So, yeah.
Okay, interesting. And yeah, the figure 10, I think it's a very interesting figure.
Yeah.
It's about like the computerization of DiLoCo. I think it was already here during like the streaming DiLoCo paper.
Yes. So this is not strictly new. This has been in other works that Arthur Douillard talked about before. Maybe just to explain to the audience what this is simulated compute utilization. Compute utilization is essentially what percentage of the time of training you're actually doing things like matmols, as opposed to kind of waiting for things like all reduces to take place. And so what we would like is 100% compute utilization of 1.0. That means that all the GPUs are being kind of used to their fullest extent, and you're not waiting around for things to synchronize. And so this is simulated compute utilization for various different models. So 10 billion chinchilla style decoder only transformer model, a 405 Llama 3, or a 671 kind of DeepSeek style model. It's just the model size that matters. It's not really the architecture underneath it. And it's simulated in the sense that what we do is we actually so we use JAX for all of this. We actually look at the underlying HLO when you start to actually compile this to understand kind of how it's laid out on the across TPUs. We use TPUs for ours, and essentially try to figure out based on that what is the compute utilization. This is sometimes a hard thing to measure empirically while something is running. Just because, for instance, if you don't have an efficient data pipeline, you might be waiting for data, but you can fix that. You know, there's some things that make it easier to simulate than necessarily to observe. But this has lined up when we've done kind of large scale experiment with the actual compute utilization that we see. Anyways, that disclaimer going on. The results in this plot are pretty simple. It's basically if you communicate less often, so H is how often you communicate. If H equals 300, you only communicate every 300 steps. You communicate less often, you have better compute utilization. And it's measured in terms of bandwidth. So higher bandwidth, you're not waiting around for stuff as much. So if your bandwidth is high enough, even data parallel can get 100% compute utilization. But when your bandwidth is very low, you might want DiLoCo in order to increase your compute utilization. That's the main message here. Things change as the model size changes, but the fundamental idea is still just that DiLoCo helps increase compute utilization quite substantially.
All right, yeah, we have the table 6 that shows like with numbers if people don't like plot.
Yes, exactly. If you are like my co-author Keith and you despise plots and you just want to freeform look at all the data simultaneously, we also include that for you. So yeah, there's just some nice observations here. You can talk about what bandwidth you need to reach a certain compute utilization, and with DiLoCo, really you can get away with a really really bad bandwidth to hit a compute utilization of 95%, for instance. Whereas data parallel needs a quite high bandwidth to do that. And so if we're talking about training across clusters all around the world, it just seems much more likely that we're going to get good performance with DiLoCo than if we were just doing synchronous data parallel training across them.
Yeah, makes sense. And some questions like related, like for example, we kind of like hit the end of the paper and like I found like the key 4 findings. Just about like the future directions, because now we have DiLoCo, we have the streaming DiLoCo, which is an optimization of DiLoCo, and now we have scaling law. What is needed like to the next steps, for example?
So some of it is actually just making it work at scale. There's like people tend to adopt ideas because they see other people using those ideas. So this is one reason I'm actually extremely excited about the effort from Hugging Face here. That's kind of on the deployment side, which is probably the hardest part, actually building the systems that make these things work. But there are actually a lot of other interesting directions in terms of research. Some of it is systems based and some of it is algorithmic. So on the algorithmic side, one of the big things is actually something you and I already talked about here. It's the fact that we don't want to have worse performance if we're training over 32 replicas instead of 8, for instance. We want to make kind of scaling to more and more replicas not degrade performance. So how do we change our outer optimization, our merging methods to make that not happen? This is kind of a really nice algorithmic problem. It's related to stuff on model merging, model souping, linear mode connectivity. All these kinds of things play a role here. And I think it's a really nice problem for people to think about. So that's the algorithmic side. On the system side, this is compute utilization. This is obviously something we care about. Something that came up in other works on DiLoCo, which is how do we design systems that can make DiLoCo even faster? And so a really simple example is making it so that the communication and the computation are overlapped. They're not occurring independently in serial. They're occurring at the same time. And that naturally leads into questions about asynchronous DiLoCo. If you have the replicas kind of asynchronously training and kind of grabbing a model and pushing updates to it. So how do you do DiLoCo, for instance, plus like hog-wild? I think is a really, really good question. And yeah, this starts to get into a realm though where the research I think needs to start pairing algorithmic ideas and interesting systems together. And this is famously not the easiest thing to do research on because you need both the people who are the algorithmic experts and you need system experts and you need them to collaborate and do stuff. It can be challenging, I will say.
And are you aware of like any other works that kind of like challenging DiLoCo in a way, or like doesn't go through the model merging, I would say, direction?
Yeah, this is a good question. I mean, I will say that I think it's actually really good for people to think about alternatives. Improvements to DiLoCo is one interesting area, but it's not the only one. One drawback about DiLoCo that's actually maybe important to recognize, DiLoCo has a lot of hyperparameters, but you can't actually recover when m equals 2, for instance. You can't recover data parallel training. There's no configuration that makes it exactly that, and that has to do with kind of independently evolving optimizer state. So what if we could have a system, for instance, that could more naturally interpolate between data parallel training and more communication efficient forms of training? That could be really nice because then you could exactly tune according to how much bandwidth you have, and go closer to data parallel when you have high bandwidth and further away from data parallel when you have low bandwidth. I just think that it's likely that we've probably not cracked it. It's probably not like the absolute ideal form of these kind of algorithms, but I think the space is quite large. So that's one thing. The second thing I'll note, this type of programming pattern where you imagine that you have different, clusters, and you can actually actively say, I'm going to do this thing with this cluster and this thing with this cluster, and I'm going to put these models together in this way. This is very different from thinking about like mini batch SGD. And I don't think that there's that many papers that really try to think about this problem space outside of kind of the DiLoCo type work. So let's re-examine it. Let's think about, is there something better that we could do? I think that's a really, really important area.
All right. Okay. So just before finishing the video, we have like question from community so far too.
Yeah.
So I will display them when I edit the video. So there's a question from Leandro von Wera. So he is asking, in which scenario will it make sense to add a layer of DiLoCo even inside a one cluster run?
Oh, wait, I saw this question on Twitter and I was actually really excited because there was something I haven't talked about yet, which is one reason you actually might want to use DiLoCo is hardware failures. We have these separate models that are training, and data parallel, unfortunately, is not particularly robust to hardware failures. You're doing optimization across all these GPUs. If one of them goes down, you have to redo the entire step. DiLoCo doesn't work like that. If one of the data centers goes down, now you have 3 replicas, let's say, instead of 4, but you can still do DiLoCo with that. So this is actually one reason that I think that you might want to use this kind of algorithm, even if you are not training across data centers, even if it's just within a single data center. You become much more resilient to hardware failures. And That's actually, I think, a really important aspect to think about is, okay, DiLoCo is robust somewhat to hardware failures. Are there algorithms that are even more robust to hardware failures?
Interesting. And there's like second question from Disciple of the Seal. His question is, it depends. I wonder if some ideas from asynchronous message passing GNNs could be used in the auto optimizer loop.
Yeah. So I will admit that I'm not a graph neural network expert. However, the transference between message passing and thinking about this kind of stuff is historically something that's already happened. I used to work with Jakub Konechny. His last name is a little hard to pronounce, but he was one of the people who really started federated learning as an area. And he actually, before doing federated learning, he worked on message passing algorithms. So this idea of a transference between merging these models together and doing message passing, I think, is a really, really useful thing to think about. It's not something that I have ideas on explicitly because I'm not like a graph neural network message passing person. But I suspect that you could come up with really interesting ways to kind of put all these models together during synchronization steps using that kind of idea. So yeah, I think that that's a really, really interesting idea.
Okay. So yeah, I think we're done with like the reading of the paper. So for findings, maybe we just go back like to the very beginning. So I think just to remember stuff like the main takeaway from the paper.
Exactly. So we're all Daft Punk fans, everybody in the world. So we have essentially, to summarize, 4 things that we found when we were doing these scaling laws. The first, which we call harder, DiLoCo's hyperparameters are pretty robust and predictable. The outer learning rate, and especially, was very, very predictable. But throughout the paper, we find that scaling laws capture DiLoCo's behavior really, really well, and scaling laws for DiLoCo hyperparameters are really, really useful, and they extrapolate quite well. So that's the first thing. The second thing, we saw this in kind of one of the first charts that we looked at. It's that DiLoCo improves with respect to data parallel as model size increases, which is really good. It means that if we care about the largest models, which we typically do, that's actually when DiLoCo is best. The third, we saw this with the compute utilization. DiLoCo is just much more efficient. It uses much, much, much less bandwidth. It really speeds things up. It improves your compute utilization. Has all these nice system properties. The last, stronger. This is one of the things that we came into this not expecting, but it popped out as a really nice side artifact. It's the fact that DiLoCo is much more robust to very, very large batch sizes, which is very useful for instance, horizontal scalability, where you want to do all your training at once instead of having to do it in serial. So those are our 4 main takeaways. Lots of other stuff in there, but yeah, it was really fun. I just want to give a shout out to all my collaborators. If you go up, this was, I'm the only one talking, but this was a huge effort among a lot of people. So yeah, thank you all to, that. And thank you, Ferdinand, for having me on.
Yeah, thank you very much for coming. All right, see you then. Thank you.